Greetings and welcome to this installment of our series regarding strength of materials and mechanics of materials. This particular video is going to cover riveted and bolted connections. Now I have this picture of this beautiful bridge up here, but if you'll notice at each one of these locations there are connections. And the most interesting thing about this and complicated thing is that these connections can fail, but they could fail in a number of ways. So if we look at another bridge connection here, these are obviously a little bit older. You see a series of rivets here that are connected to these gusset plates, and each one of these is connected to something else with a number of these, and it's calculated and make sure that if it fails in a certain way, or it doesn't fail at all, at least over a certain period of time. Now, these are rivets. This is in general how they are put together. You might already have a head, and then you put the rivet through holes into workpieces, one piece of metal here and another one here, and then you have a die that comes down and smashes it. And the resulting connection can be very strong. The material inside here actually expands so that it fills that space. And the thing is, though, is that these pieces of metal still can shift a little bit until the one bears on the other, and they might be shearing this rivet. If you have a bolted connection, such as being shown here, if it's done right in what's called a slip critical connection, then the two faces never shift, they never slip. And that requires special design and manufacturing and assembly techniques, but it can be a very efficient, very effective way of connecting these things. Well, here we are on failure modes. This is a nice slide that I grabbed off the internet here. And this shows shear failure of a bolt and shear failure of a plate. Notice how it's shear, but in different ways. So you've got failure of the connector and failure of the connected parts. So for this particular problem, we're going to consider shear failure of the bolt, of the plate, bearing failure of the plate, and tensile failure of the plate. Notice how this is cracking right down where the hole is. Now, bearing failure of the bolt, or for that matter the rivet, is very rare because usually this material that's making up the bolt is much harder, stronger than that makes up the plate. So this is not usually a consideration. Same thing here is that bending failure of the bolt is relatively uncommon because the moment arms are so small in here. Tensile failure of the bolts, though, depending on how this is designed, can be an issue. But for our particular example, it's not. So we're going to consider shear failure of the bolt, and of the plate we got shear failure, bearing failure, and tensile failure. Here we have a lap joint. Now we have a 1/2 inch thick by 2-inch thick plate here that is connected to two 5/16 thick plates here. Now this is a good design because the force is evenly distributed here and here and split between these two, and they balance out these rivets. It's possible because of the distance between these two, if you just had a 1/2 inch plate to a 1/2 inch plate, that the rivets can get twisted and greatly increase the stresses and possibly cause a failure. This is a balanced way of making the connection. Now notice also that between this one, which is 5/16, and this one, which is 5/16, it adds up to greater than 1/2 inch, and so we would be looking probably at this 1/2 inch piece as the weak link compared to these two. Okay, so this is a lap joint that has a 2x3 pattern to it, and the dimensions are as such where you've got 3/4 of an inch between them here, and 7/8 of an inch between them vertically, and from the center here to the end is 0.625. By the way, the same thing goes for the other plate here. From the center of the hole to the end is 5/8 of an inch. Now, these curvy areas simply mean that this material continues on elsewhere. Now, to look at the rivet, this is what my rivet looks like. It may not actually end up this way. It's maybe too flat here, but this is what the rivet looks like on the inside. This is what the connector plate looks like without being in the assembly. So looking back at the assembly, we need to know a couple more things. This is kind of hard to see here, but if you'll notice, you just click on it. There we go. This is the diameter of the rivet. Okay, and the other dimension that we need to know is the diameter of the hole. Now, if we hide that particular rivet, you'll see that the diameter of the hole is indicated by this 0.313, which is 5/16. Well, where did that come from? Well, for clearance to get the rivet through the hole to begin with as part of the assembly, there needs to be some kind of clearance, and we use an extra 1/16 on top of the size of the rivet to get the size of the hole. So this is 4/16, this is 5/16. Now, to review our failure modes, this shows you what it might be like inside. So if this plate is pulled this way and these two plates are pulled the other direction, then this plate could or will contact the rivet right in this space. This plate would contact these rivets on their surfaces right in this area, and these two plates, the upper and lower plate, would contact here, 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 and here. So there's going to be two major types of stresses going on here. First is shear. Right here is a shear plane, and right here is a shear plane. So these rivets would actually be cut, sliced right at those locations, because this one's pushing that way, this one's pushing that way. Another one is when they actually contact. They are bearing, they bear on each other. So it's a contact stress. So it's a bearing stress in this situation. Okay, to show you the shearing planes again, I'm going to bring this down just about here, and you can see if this top plate continued moving, it would literally cut these things off. The same would happen down below here. If I were to look at the tension across this cross-section of this particular plate, notice how these holes that are going through the plate reduce the cross-sectional area available to withstand the force. So we would have a force, P, divided by the cross-sectional area here, here, and here, that we would have to add up. Again, not the entire cross-section for this whole entire rectangle, because the holes are cut. So we have to consider that as a tension problem. And then finally, if you'll notice, there is a certain amount of material here that is needed to withstand the stresses at the very end here. If I were to change the dimensions, something that looked like this, then we would have a lot less material here, and this could possibly shear off and fail in that way. So again, we've got 4 different failure modes that we need to consider. There we go. Here are the forces. So this is the force P we're going to talk about here. And these two, we're assuming are going to be half of P each. So it's going to be evenly distributed. So you can look at it that this shear plane here is only taking half of P because this is splitting up here and here. Or all the shear planes, both of them, are taking the full load of P. Okay, hopefully you get the idea there. All right, so let's write that in. So this one's half P, and there's another one here that's half P. So our plate material is A242 steel, and our rivet is some carbon steel material. Now I'm using the tables in the textbook that we used in my class, and I'm not going to put the tables right up here for you. I'll put the references up if you're going to be following along with the book. Otherwise, you'll just have to take my numbers and my references here as a given. But it is important to know that there's a lot more beyond just quote-unquote carbon steel. Of course, there's some many different grades and so on. But this is just for simplicity's sake. Okay, so we are going to find, first off, the failure mode. Is this going to fail at the rivets, in tension, in bearing, what? If we find that we need to change something so that we can take our load, what should we change? And when all is said and done, what's our factor of safety? All right, I know that I'm going to have to look some stuff up. So I'm going to put in a category here, look up, but when we run into those things, we'll put them right here. Okay, for shear of the connectors, we need to simply calculate how many of them there are and what it's going to take to cut each one. Now, P allowable I'm using as the overall force P for the whole system. So that's going to be equal to the allowable force on one rivet times the number of shear planes. Okay, and in this case, our rivet, we look up carbon steel rivet and it's a quarter inch carbon steel, and we look that up in table 13.2, and the allowable force for a carbon steel rivet of a quarter inch size is 700 pounds. Again, that's table 13.2. Now, if you have a newer edition or a different edition, it might be something different, but it's in that table there somewhere, I hope. And now notice this is in double shear, and we have 6 of these rivets. That means we have 12. So that is 700 pounds times 12 gives us 8,400 pounds. You can see right off the bat that that's just not going to cut it with 10 kips of applied load. Okay, well, we've got to look at the other ones too to see what's going on with them. So next is bearing. And for bearing, we have to add up all the bearing surfaces. Now, again, the half-inch plate is somewhat smaller than the combination of the two 5/16 plate. So we're just going to look at the half-inch plate. Now, the allowable bearing force is going to be based on the allowable bearing stress. Stress bearing allowable, so you might call it stress ball, times the area in bearing. Well, to calculate these things, we look up what the allowable bearing stress is going to be. And that's in table 13.1. So in table 13.1, you see for connected members, all alloys, allowable bearing stress is 1.2 times the ultimate strength. And the area in bearing is going to be the total number of these things, number of bearing surfaces, times the thickness of the plate, times the diameter of the rivet. Now, we use the diameter of the rivet because there's actually going to be a higher stress right where the rivet contacts first on the one edge, and it's going to lessen as it gets out. But we simplify it conservatively by simply multiplying it by the thickness. There's actually going to be more area in bearing, but with ductile materials and a conservative estimate such as this, with only the diameter of the rivet concerned rather than the entire diameter of the hole, this is a reasonable estimate. And we plug in 1.2 times SU. Oh, what's SU? Oh, we've got to look that up. Okay, so going to the appendix for structural steel, we find that SU, or ultimate strength, of a 242 steel is 70 KSI. So 1.2 times 70 KSI, and multiply that times the number of bearing surfaces. Now, this is not the shear plane thing, this is just bearing surfaces, so we only have 6 of them, times 6 times the thickness, which is 0.5 inches, times the diameter of the rivet, which is a 1/4 inch, and we end up with 63 kips. So we would have to apply 63 kips before we got some failure in bearing here. So that's much higher than the shear, and it's much higher than our applied load. So we're good in bearing. Tension at the holes. Okay, this is where we have to subtract out the holes from a regular tension calculation. So our allowable load is our allowable stress in tension times the area, call it the net area, the area that's left over after we drill the holes. And again, going back to table 13.1, our allowable tensile stress is 0.6 times the yield strength. And these are based on AISC specifications. Very important that you follow the AISC code for any kind of steel construction. These are the folks that have done all the calculations and know what the right factors of safety should be, and so on. So if you follow those guidelines in their handbook, you should be in very good shape. It does get complicated, but that's the way it needs to go. So these factors, the 0.6 times SY, the 1.2 times SU, those are all taken from this AISC, but again, in this situation, it's simplified. In your situation, it's probably going to be more complicated and need more of the code book. Okay, so our net area is going to be the thickness, because that's the same on all of them, times the width. That's what it normally would be, just the thickness times the width, but the width has 2 holes taken out. So a small n, not 6, just 2 holes in this cross section here. So this hole and this hole. Okay. So we've got 2 holes taken out of that cross section. And so that's nx here. Then nx is multiplied by the diameter of the hole, not the diameter of the rivet. So nx has to be multiplied by diameter of the rivet plus that additional clearance I mentioned before, which is a 1/16 of an inch. Okay, so another parentheses here and close it up there. All right, let's put this all together. So for tension, we have our allowable tensile strength is 0.6 times our yield strength. Oh, we got to find that too. So you go back to that table in the appendix, and the yield strength of A242 steel is 50 KSI. So we'll multiply that times 50 KSI. The thickness, again, 1/2 inch, times the width, which is 2 inches, but the width is reduced by 2 holes times the diameter of the rivet plus 1/16 of an inch clearance. Okay, you put all that together, and the tension at the holes gives you an allowable force of 20.6 kips. That was a little tedious, but we got through it. Notice the 20.6 kips is a lot smaller than the 63, but it's still well above the 10 kip force that we want to apply. That's fine. Last but not least, we have end tear out. Now, there are a variety of ways of considering end tear out, but a rule of thumb is that the distance from the edge of the hole, which you can't see here, to the end here, so this distance right here should be in a ratio. So that distance, I'm going to call it the end length, divided by the diameter of the hole should be greater than or equal to 1.5. Now this factor of 1.5 could depend on a variety of things, the materials, how they are cut, how they are assembled, many different things. Sometimes it might be 2.0, but we'll stick with 1.5 for the sake of simplicity here. So if you'll notice, we have an end length here of 0.625, but this is to the center. So we're going to have to subtract out half the diameter. And that's the diameter of the hole, not the rivet. So here's the rivet. Add 1/16 and take that whole thing and divide by 2. So that's the radius of the hole. So that'll get us back to where we need to be here. And the diameter of the hole itself is this thing again, 0.25 inches plus 1/16 of an inch. And that gets us to 1.5, which coincidentally is greater than or equal to 1.5. Now we should note that this is barely okay. All right, so if we were to redesign this, we might want to put a little bit extra space on there, but this should be fine for our purposes. Okay, going back through that then, we have shear, which did not come out okay, bearing, which was just fine, the tension, which was just fine, and the end tear out, which barely is okay. So all we want to do here is redesign our shearing of our rivets so that we have at least larger than 10 kips. Now, if we go to table 13.1, you'll see that it shows a number of bolts. So if I wanted to replace these rivets with bolts, this might work out fairly well. So let's go do that, and you'll see how the bolts are a little bit different. So we're going to redesign it. Place rivets with, we're going to look at the A307 bolts. So the rivets showed the actual force that could be placed allowably on the particular rivet. The information we're given for the A307 bolts, or for the other bolts for that matter, is a little different. Our allowable shear stress for the A307 bolts is 12 ksi. So we have to consider the size of the bolts as well as the material here. So our allowable force is going to be our allowable shear stress times the area in shear times the number of shear planes. So our allowable shear stress is 12 ksi times our area in shear. Well, we've got to consider pi over 4 times our 1/4 inch bolts times 12 circular cross sections, and that gives us 7.1 kips. And guess what? This is not an improvement over our 8.4. So we should probably look at some better materials. Let's look up what it is for A325 bolts. And our allowable shear stress there is 30 ksi. So definitely a bump up there. So our allowable force is Again, allowable shear stress times the area in shear times the number of shear planes is 30 KSI times pi over 4 times our 1/4 inch diameter squared times 12 circular cross sections yields 17.7 kips, and that is definitely larger than the 10 that we were hoping to take, so that is good. Finally, we need to calculate our factor of safety after our design is done. That's fairly easy. Calculate what we can safely take, divide by what we are designing to take, and we get basically 1.8. Okay, so for this problem, we went over what types of stresses, how they impact a connection, how any one of them can be a source of failure. So you need to calculate all of them to compare and see what's going to fail. The other thing is that you might want it to fail in one way rather than another. For example, if you designed it to fail in shear of the rivets, you might notice that ahead of time if you compared to failure of the bulk material. And you'd want that so that you could have some warning. So we found the failure mode by doing all those calculations for the shear, the bearing, the tension at the hole, and the end tear out. We found that our design held up fairly well, except for the shear of the rivets. So we redesigned it using bolts. We found that the 1-bolt material was actually going to be worse, so we changed our material to something a little bit stronger, and that came out to work out, and our factor of safety was reasonable as well. The tough parts here are making sure you've got all of the necessary information here and figure out what's what. The tension at the holes is a little complicated, but when you remember that all you're doing is you're subtracting out the hole, and you've got to consider the clearance and what exactly is the cross section here. We only have 2 in the cross section. Then again, breaking it down little by little, then putting it all together is the way to success in this type of problem. Well, I hope that this video has helped you understand stresses on connections and has helped further your education in strength of materials and mechanics of materials. Keep watching so that you can learn more and give me feedback as to how I can do better. Thank you.